Hi, everybody. I would like to share with you today the idea of delta hedging in the Black Scholes model, and I would like to perform the Monte Carlo simulation to show how good is delta hedging. Is something Black Scholes model tells us that with delta hedging, with dynamic delta hedging, we can the option provider can hedge all the risks. Let's see how good is this model. Can we hedge all the risk with delta hedging? I will try to answer this question with help of the presented simulation. So in order to provide this simulate the results, I created the model which uses the Black Scholes formula. We start with we need the current price, is current price of 10 in our model at the moment. We enter this in B4, then we have the strike price in B5, expected term, we go for 1 year. In B6, volatility of 40%, dividend yield of 4% entered in B8, then the risk-free interest rate of 3% entered in B9. The Black Scholes model calculates then D1, D2, ND1, and D2, and we have the option call premium calculated in B15. In our model, we will look the hedging activities which happen during 1 year. So we want to know the results as per end of the year. Therefore, we calculate continuous interest for 1 year for the option premium of 148 and obtain the results of 153 or 152.80, which we will be using to compare against our hedging activities. To create our model, we need the assumption about the return and volatility. These are the annual numbers. Since we want to make a daily, simulate daily prices, we have to calculate daily return and daily volatility. Our model is in the area, the row 22 is the description. In the row 23, we start with the model where we have the date. In A23, the period. If in B23, we take the stock price from option price model. In this case, the number is $10. We calculate the delta according to ND1. Then in E24, we have the delta change. Since it is the first transaction, the full amount of delta is delta change. And then we have to buy, in this case, according to delta, 0.5695 shares at the price of 10. So we pay 5695. However, our shares carry the dividend of 4%, and the interest is only 3%. So after 1 year, the amount which we will have to repay, which will be even lower than the amount what we borrowed, because we make some income or coming from dividends. So we have to repay in 1 year from now $564. The second day, let me explain the second day. The second day, okay, we have increased the day by 1. The period is reduced by 1 day, and now we are obtaining our first simulated stock price for To calculate the change, we use the well-known formula, which assumes the drift plus the volatility. We use the norm inverse function in Excel to calculate our probability. We use the random variable, which is calculated automatically by Excel as any possible variable between 0 and 1. And then according to assumed distribution, we have the return of as per cell C18 and volatility as per C19. And okay, since it is a probabilistic function, every time we press enter or press F9, the calculated stock price will change. We calculate the new delta, which assumes now uses the new current stock price, not of 10, but of 10.27. Since the price increase, we have the delta increases, so the delta change leads to additional purchase of stocks according to the delta change. And in 359 days, since we assume the year of 360, this will result in our costs, hedging costs, which then will be added together and show us the total costs of all hedging transactions during the year. It is showed in the cell F2021. We see here also the last price as per after 360 days. It will be the last price. It will be 11.36. So at the price of 11.36, the option will be exercised. The option writer, in this case, who is checking he's applying the dynamic hedging, will incur the costs of 11.47, but it will obtain from the option buyer only $10. So it is has the cost of 11.47 minus 10, which he obtained from him, of 147, but we obtain he has obtained the premium of 152, including the compound interest. So the net hedging cost is the difference between premium received and costs of delta hedging, results in the gain of 6 cents. So we have the very positive results of this delta hedging. We don't, with Excel, we don't not necessarily need make all hedging transaction just year after year. We can make with the help of the special function. We can hedge. Or we can simulate the results for 18 years in one just with one move. What we will do, we will simulate now the cell H19 318 times with help of the table 1, data table 1. We don't enter anything, nothing in input cell as the column cell, any blank cell, doesn't matter which, but it has to be blank. and the computer calculates, simulate for us the results for, we had here 1 year for 318 years. We could do this for 1,000 years. In any case, you see the results of this simulation after 318 years. On average, you will get 3 cents more than you would receive from the premium. So from the option writer, it is Delta Hedging offers very good strategy. On average, for in this case 318 years, you will make on average profit. But keep in mind, when I go through all of these years, some years, not many, more or less one per 100 years on average, you can generate quite big profit or loss. Okay, in one year, you result in almost $1 loss, or we have almost $2 profit results from Delta Hedging versus what we receive as the premium. So on average, yes, Delta Hedging fulfill the promise as the calculation as per Black Scholes formula is correct, but every 100 years it can the situation can look different. By the way, here is the I also graphic which shows the simulated stock price for each year. When I press F9, no, somehow doesn't want. Now it has changed, so prices are changing every time I press F9. I did some couple of calculation which I would like to share with you, and this is a big advantage if we can simulate something. With simulation, we can get better understanding about the model or how good the model is. Already I make the statement that it showed that in this 1 year, what we simulated, we received on average very good. Not on 1 year was quite good, and for 300 years on average, we generated 6 cents better than when we receive as the option premium. But the option premium, the results of the simulation depend also about the assumption, what was the volatility and what is the return, assumed return. So I made the simulation here. I kept the volatility in the first table, but I kept the, I show this here, you can see on the screen. I show the volatility of 40%, return in the first case 20% per year, return of 0, and return of -20. And we see here, when we do a delta hedging according to D1, as we were showing here, as I was showing all the time up to now, on average of 318 years, the results are better by 1 cent. When we reduce the volatility to 0, but we keep volatility the same, but we reduce the return to 0. The results on average will stay by 2 cents better than what we obtain per premium. And if we reduce the return to -20, the results are better by 4 cents. However, the Black Scholes model tells us D1 is the delta. It is what we should use as the hedging for our portfolio. But let's assume that we do the hedging not according to D1, but according to D2. When volatility is 40% and return is 20%, the results with hedging according to D2 is by 17 cents worse than what we obtain as the premium. When the return is 0, the results are still worse than what we would obtain, as the premium. But when the return is minus 20, now hedging according to the D2 is shining. The results are better. So we see the results of the model, outcome of the model depend on the assumption what was the volatility and what is the return. Let's look at the possibility of changing the volatility to 20%. We have the volatility 20, 20, 20, and return is 20%, return 0%, and return minus 20%. We perform the hedging according to D1. So in the first case, we have plus 0.73 cents, 82 cents, and 69 cents. However, if we would increase D1, every D1 by, I was simulating with goal, seek what was the best number by which I should increase D1 to perform best. And it came out that if I would increase by 0.54752 and then calculate and D1, which is the delta, I would obtain better results. Yes, but not in every case. I would obtain better results when the return would stay would stay at 20%. So the results would be by $1 better. Almost the same as with D1 as D1 by null return, but when return would change to negative return with minus 20, this increase of D1 would result in worse performance than hedging according to D1. In any case, we have received premium. It is easy to explain what happened here. We receive premium based on volatility of 20%. Now we simulate results with a volatility of 20%. So model calculated cost when volatility was 40, and now we have volatility of 20. So according to how important is volatility, this kind of results were expected, but it is more profitable now because the actual volatility was substantially lower than assumed volatility. But how results will look like if the actual volatility is higher than what we have assumed? We have assumed in our model 40% volatility. Now we simulate simulate the price changes with the volatility of 60%, and we have three cases: return 20, return 0, return minus 20. So if we just make the hedging according to D1, and the return is stay with 20%, we lose 52 cents. With the return of 0, we gain 82, and with return minus 20%, we gain 0.76. Since comparing to these two different other possibilities of increasing D1 by 0.54 or performing hedging instead of according to D1, according to D2, D1 hedging, dynamic hedging according to D1 shows the best results in most of the cases. So having D1 as the delta hedging seems to be in the majority of cases the best decision. I only performed a couple of simulations, but we can see the delta hedging can provide protection when the reality is as per model assumption. But if expected return or end volatility differs from assumptions, the results might be quite different. And even if the results with the same assumption as per model occur in some years, let's say in our model every 100 years, the results can be substantially different than projected or indicated by the model. I hope you like it and you learned something. Thanks for listening.